Okay, so I think we can start, and today we are actually going to start with deep generative models. I mean, till now we were mostly reviewing probably theory and statistics, but starting today we will go into deep generative model, and we will talk about one type of generative model today, even not completely, just we'll start talking about autoregressive generative models today, and but we'll not be able to complete it. And on Friday there is no lecture, so we'll next meet on next Tuesday, 27th, and then we'll continue on whatever we discuss or wherever we leave uh, today. Okay. So with that background, let us start. So we have already discussed and defined what is a generative model. So can you remind me what is a generative model based on what we discussed earlier? It's a class of machine learning model that attempts to learn the distribution, right, from which the data is generated, and use that to generate new samples, sometime even to learn some common features or unsupervised representation learning as we call it. And it has a lot of application. Apart from generating new data, you can use it for anomaly detection, I just said feature finding common features and all of those things, right? But so let me write it down once more. So generative model, so it's a class of machine learning model that attempts to learn the distribution. And when I say learn the distribution, I will remind you that it's either implicit or explicit. You need not always learn the distribution explicitly. It is possible, and it will happen in many cases, that you will only learn the distribution implicitly, and you are just able to sample from it, but you do not have a form for that, right? We have discussed it, nothing new. Learn the distribution, that attempts to learn the distribution from which the data is generated, right? And obviously, once you learn the distribution, you can use it. The objective is to use it to solve different types of problems, generation of new sample, anomaly, and all of those things I was talking about. Now, if we have to write it mathematically, what does it boils down to? So mathematically, it means that given some data, some training data that I have, which let's say is of the form x1, x2, and maybe I have n such samples, xn. So given that I have n data, x1 being the first data, x2 being the second data, and xn being the nth data, give we want to learn probability of data, which is in this case or in many cases will be x1, x2, x k. And I'll talk about what is this x1, x2, xk, why is it different from, I mean, what is the difference, right? So this x1, where a1 is in the subscript, is different from x1, small x1, where 1 is in the superscript. When 1 is in the superscript, it means one data point, right? Think of anything. So x1 can be an image, right? So x superscript 1, the data. One data can be an image. Think of one sample from your MNIST dataset. It's an image. X2, x superscript 2 is another image. So that's what x superscript 1, x superscript 2 denotes. X1 is the feature in an image. So if I talk about the MNIST again, MNIST we know that is 28 cross 28, 784 pixels you have. So in that case, x1 is my first pixel point. x2 is the second pixel point. And xk in that case, k is equal to 784. So xk is the 784th pixel point, right? So just to give you some context, so this sir, what you are seeing right is different data, right? So these are like x1 superscript 1, x superscript 2, x superscript 3, and like that I have 9 data. So I have my capital N is equal to 9. But each of these x1, x2, x9 is having a size of 28 cross 28. So each of this is having 784 pixels. So that capital K that I wrote is equal to 784 if I vectorize it, that is. So x1 is my first feature, which is like the first pixel point. x2 is my second feature, like the second pixel point. But x superscript 1 is my first image, right? So this distinction keep in mind because it's very easy to confuse between these two things. So I wanted to make it clear at the beginning itself, right? So we want to learn, so that's why we want to learn the joint distribution over all the pixels, which means if I draw a sample from it, from this joint distribution, I will get a sample of dimension 784, which if I reshape will be of dimension 28 cross 28. So sampling from this distribution is like sampling an image. Sampling from this distribution is equivalent to sampling an image in this example, right? So I'll write it here that note that x1, although I'm writing it like this, is something like itself is having x 1 1, x 1 2, x k 1, right? So each of the image is having this dimension. Each of the image is a k dimensional vector, or not image. Each of the sample is a k dimensional vector, right? Which to relate, think of it like the image. But it need not be image, it can be a time series. It can be just a vector also. So it need not be image, but image is what you will easily relate to. So I'm taking the example of image, but it can be, a time series data. So x1 is like one time series. X sub superscript 2 is like another time series. And then time series, we have time steps. So each data, a time series has maybe k time steps. So you can imagine it like that as well. Clear? What is x superscript 1 and x subscript 1? The distinction is clear, right? And the objective is also clear. We want to learn the joint distribution of x1, x2, x3, x4, xk from the data. From the data, I want to learn the joint distribution of x1, x2, x3, where each of this is like one feature in your data. It's like a one time step in your time series, one pixel in your image. You can think of it like that. Any question? This is clear? Okay. So if this is clear, this is what we want to learn. This is the goal of any generative model actually. This is nothing specific about what we are going to discuss today. But this is the goal of any generative model. And starting today, we will talk about different techniques that allows us to learn this P of D. or learn this P of x1, x2, dot 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 xk. So starting today, we're going to talk about different algorithms, different frameworks that allow us to learn this joint distribution, which means all of those will be generative models by definition, because they are learning this, right? Okay. So now we're going to start talking about a class of, and it's a class of, it's not a single model, a class of generative model known as autoregressive generative model. Okay. We're going to talk about a class of generative model known as the autoregressive generative model. Okay, we're going to talk about that. Autoregressive generative model, by definition, is based on the principle of autoregression. That's why the name autoregressive generative model. Straightforward, right? But where is autoregression coming in the fact that I want to learn this joint distribution? I don't see any autoregression in this joint distribution. There is none. So how come autoregression is coming into picture? Actually, there is autoregression if you think about probability decomposition. Remember probability decomposition of joint distribution? We did it last time. If I have to write this joint distribution using the product law, how will it look? Probability of x1, probability of x2 given x1 multiplied by x3 given x1 x2 dot 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 x k given x1 to k minus 1. Is that not autoregression? It is like autoregression. You will do one at a time. You know x1, and then condition on x1 you are doing x2. Condition on x1 and x2 you are doing x3. So it's a autoregression kind of expression. I mean, ultimately it gives rise to the Markovian expression. I mean, if I do some assumption, right? So in this, the basic idea is that we will be using this probability decomposition. And then from there we will see how can we sample this joint distribution from that decomposition. Okay. So using product law, what we get is probability of x1, x2. Okay, keep in mind that although I am writing it as probability, actually P is distribution, by the way. I mean, we want to learn the distribution, not the probability. I mean, so P here is distribution, keep that in mind. I am saying distribution but using P, so it's very easy to confuse. So P is actual distribution. Anyways, whatever applies for probability also applies for distribution. So nothing will change as such, but soon it will become even more clearer that it is a distribution. But just to make things clear, P is distribution, and we are interested in learning the distribution, not the probability. I mean, knowing the distribution will become probability eventually, but what we are aiming for is to learn the distribution. Okay, so x1, x2, xk, I can write it as probability, or P of x1, P of x2 given x1, P of x3 given x1, x2, and you continue. The last term will be P of xk given x1 to k minus 1. Right? This is fine. If this is fine, can I not say that learning the distribution on the left hand side is equivalent to learning each of these distribution on the right hand side. If I can somehow learn these distributions on the right hand side, I can use them to compute the distribution on the left hand side, right? Correct. So in autoregressive generative model, we aim to learn the conditionals. Most of these are conditional, so I can call them conditional distributions. So in autoregressive generative model, we attempt to learn these conditional distributions, and there is one term which is like a prior, but it's not really prior in this case, but it's the marginal basically, right? Distributions and P of x1. Now keep in mind that this decomposition is not unique. It need not be x1, it can be x2, and then you can start from x2 and do all this business. So it's a choice you will make that from where to start, and since you will be learning, most probably that will not matter in most cases, but it's a choice you are making. I mean, you can choose to start from k, for example, xk minus 1 given xk, and so on and so forth. Or in a practical scenario, you can decide which is your pixel number 1. Whether it is the middle one, top left, top right, bottom left, bottom right, some random number. It's a choice you will make that from where to start. Yeah. Not much. It will not affect much. Okay. So generally what you will do is think about the MNIST, and I was coming to that anyways. You will probably start from bottom, top left, because that one is mostly black, right? So finding that one is like almost with probability 1 you will find that one. So that will be known. So finding out this probability of x1 is actually not difficult. You can get it directly from the data. Or everything else you will get from data also, but maybe not so straightforward. Finding the conditionals is actually challenging, because it will be almost impossible to find what is probability of pixel 2 given pixel 1, or pixel 3 given x2 and x1, or even pixel 784 given 1 to 783. So it is the conditional that will create challenge for you, not really the prior. I mean, it's not prior, but not really the marginal. The marginal will not really create problem. For example, look into the MNIST data set, right? Top left, pixel 1, let's call it pixel 1. It's almost black always with probability 1. So P of x1 will probably always give you black, right? So, and if you start from there, it's fine. It's absolutely fine. What does P of x1 actually mean? Is it like probability of that pixel value? Probability of pixel? Probability distribution of the pixel? What distribution that pixel, whatever you call pixel 1, that follows? What is the probability distribution of that? Okay. I'm saying for this example, it is easy. Ultimately, we will be learning it from data. Everything will be learned, and that I will not talk about today. That is for next lecture. But ultimately, learning is never easy. I mean, as simple as that. But for this example, it is easy. That's what I'm saying. And also, it is actually easy to find that one, because if it is even changing, you have a 10,000 data set. Just do the MLE. Just count how many times what is coming. Find the ratio. You can set it to be that. When I'm saying easy, I don't mean that it will always be 1. When I say easy, you can just find the ratio, because you have in 10,000 data points, 60,000 data points in MNIST. You just count what is the number of, let's say, black at that point and divide it by 60,000. But this will only happen for x1. For x2 given x1, you cannot do that now. You will not always get that thing. You will, for x 784 given 1 to 73, you can never do it. So in that sense. Correct. Hmm. No, because ultimately that pixel will don't tell you anything. It's a joint distribution that will tell you everything. And in the joint distribution, it does not matter where you start from, unless and until your problem is becoming highly ill-posed. We don't care about what is the pixel probability of or marginal distribution of middle pixel. We don't really care. And that tells us nothing actually. What we care about is what is the joint distribution. Joint distribution of every pixel. And when I'm talking about joint distribution of every pixel, it will not matter. Because even if you start from the middle, you can find it out. Okay, 60,000 find the ratio, that's fine. But then you have to do the conditionals, other conditionals. And that has to be done. And ultimately, it's the product, the left hand side that will matter, and you need to find the left hand side. Okay. So in autoregressive general, we aim to learn the conditional distributions and P of x1. This is what we aim to learn, right? Okay. So now, from here onwards, for some time, I'm going to only talk about the MNIST dataset because that will make it very intuitive. And but then I will generalize it to, let's say, a continuous. Yes. Okay. So now this same problem, let us talk about with MNIST dataset in our mind. Okay. MNIST dataset, K becomes 784, N becomes N, let's not go that number, N becomes N, so N I'm not going to change. Okay. And I'm only going to talk about MNIST dataset. So if it is MNIST dataset, what is the probability distribution of x1? I don't want the exact distribution, but what is the distribution family? There are different types of distribution, right? Gaussian, and then let's say Poisson's, and there are different, right? P of x1 will be Bernoulli. Why Bernoulli? Because it's either black or white. It's either failure or success. So P of x1 is Bernoulli distribution. Everyone agrees that P of x1 is Bernoulli distribution? Because that pixel value will be either 0 or 1. Let's call black as 0 and white as 1. It will always be 0 or 1. And it is true about all the 784 pixels I'm talking about. Right? So P of x1 is Bernoulli distribution. P of x2 given x1, what is the distribution? What is P of x2 given x1? Given that x1 is, let's say, white or black, one of that, let's say white, given that x1 is white, what? Not independent. It's actually not independent, it's spatially related. So the question is that P of x2 given x1. Now x1 is, you have observed, let's say I have observed to be black. So given that x1 is black, what will be x2? Now what can x2 be? Black or white. So what is the distribution P of x2 given x1? Bernoulli. Same for the last one also. Given that you have observed this 783, the 784th one will either be black or white. So each of this distribution is a Bernoulli distribution. What we do not know is what is the probability of white versus black. So the parameters of the Bernoulli is not known to me. That is unknown. But each of this distribution is Bernoulli. Is everyone on the same page with me on this aspect? That each of the pixel will be Bernoulli because it will be either black or white. So it's either success or failure, and therefore it's Bernoulli. Right? So considering the MNIST example, it is trivial, it is trivial to say that all the distributions on the RHS are Bernoulli, right? And because all of these are Bernoulli, I can write the joint distribution as product of Bernoullis. Um, so P of x1, x2, xk, right, not n, is equal to, and xk is 780, k is 784 for this one, right? This is Bernoulli, so B here is Bernoulli of x1 with parameter alpha 1, where alpha 1 is the probability of getting, let us say, white. So 1 minus alpha 1 is the probability of getting black, multiplied by Bernoulli x2 given alpha 2, but alpha 2 is a function of x1, because it is probability of x2 given x1. So whatever what that alpha 2 value is a function of x1, right? It will come as a function of x1, and we'll see how it will come. Okay, multiplied by Bernoulli. What is the third term? X3 given alpha 3 function of x2, and you can continue like that. The last term will be 784. In this case, I will write k, Bernoulli xk, k is 784, alpha k function of 1 to k minus 1. Okay, where alpha 1, alpha 2, alpha 3 are probability of success, and 1 minus alpha 1, 1 minus alpha 2, these are probability of failure. And these alphas are unknown, by the way. These alphas we do not know, right? We do not know these alphas. We need to find out this alpha, and we don't only need to find out this alpha, we want to find out this alpha as the function of uh, the conditional variables, right? Any idea how am I going to find out this alpha? Obviously not discuss that today, but how can I represent these alphas, specifically alpha 2 onwards, so that it is easy for me to visualize how we will be doing it next time. Any idea? It's a classification problem. We'll use logistic regression. Think about a sigmoid function, and then inside that it is some linear function of the input variables. So for example, if I take alpha 2 of x1, that will be sigmoid of W transpose x1. And sigmoid gives you value between 0 and 1. So it's like it will give you a probability value. Right? So this alpha of x, we will model it, one of the option. This is not the only option again. One of the option is to model it like a logistic regression problem, like a classification problem, where you are trying to find out what is the probability of success. Right? Yeah, go ahead. Okay. So one option is to represent alpha as let's see. Let's take arbitrary alpha. Let's say alpha j. Okay, alpha j is some intermediate alpha, right? Some arbitrary alpha which is between 2 and k, obviously. I mean, one is independent, so one I don't care about, but between 2 and k. So alpha j. Alpha j is will be function of what? 1 to j minus 1, right? So in some books, some papers, there is another notation. So let me use that also so that you are familiar with that. X less than j minus j. So in some papers, some articles, they rewrite it like this, which means it is function of all those x, which is less than j, which is 1 to j minus 1. So you can write x1 colon j minus 1 or x subscript less than j. Either works, whatever you prefer. I actually prefer 1 to j minus 1, but I thought that I should introduce this also, so I brought it up. Okay. So alpha 1 to j minus 1 is equal to, remember the logistic regression, we did it in the practical, right? Thursday, last Thursday, right? It was sigmoid function, sigmoid, and then inside you have a linear model, right? So let's denote the parameters that are inside as beta, because alpha I have already used. So let's call it beta j 0 plus j I cannot use. No, I can use. So here I cannot use. Plus summation I is equal to 1 to j minus 1 beta j I x I. See what I have done? Simple linear term. It is basically saying beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta j beta j minus 1 xj minus 1. That's all that it is saying, but I have just written it in a generalized form so that I don't have to write for each of these terms. That's all I have done. This is clear for everyone? It's simple. The parameters will, the parameters will, each one will have, yes. So the parameters will be n square in the order of n square or k square by 2. So I will come to that next. But yeah, you are right. Each of these conditionals will have their own parameters. So you can imagine what will happen. And the number of parameters for each of the conditional is not same, because it is function of different numbers of variables. Clear? So if this is alpha, I can go and put it into the Bernoulli distribution, and then my Bernoulli distribution is complete. And what I want to now compute is beta. So my original objective was to compute the joint distribution, not alpha. Original objective is always to compute the joint distribution, which I decomposed, and I said my objective is now to compute the conditionals and the prior or something like prior. Okay. Then I said, okay, no, not the prior. I know that the conditionals and all of those actually are Bernoulli. So my objective became computing the parameters of the Bernoulli. And now from there, now my objective is to find out beta. So from finding the joint distribution, from conditional, then from Bernoulli's parameter, we are now in a position where we want to find out parameters of logistic regression. Multiple logistic regression, but parameters of logistic regression nonetheless. That's all we want to find out. Okay. How we will find out, again, I will not talk about today, but we'll come to that later. But you can imagine that this is what we need to find out. And if we can find it out, my joint distribution is exactly, not exactly, it's known. It's not exact because this is not exact. Any question? Yes, yes. Beta. Yes. So now the learning problem is, or the training problem will be, when you talk about it, is to find out beta, at least for this problem. Okay, clear? And if that is the case, you know that I'm not writing it, but you know how to the joint distribution will now look like. Each of this will be like that. Okay. Now, if this is the case, we're talking about parameters, right? So let's talk about that. So let me see. What is the total number of parameters of this model? Any idea? What will be the total number of parameters of this model? Let's go step by step. Alpha 1 is one parameter. That's the constant. For alpha 2, how many parameters will I have? 2, beta naught and beta 1. For alpha 3, 3. So it is 1 plus 2 plus 3 plus dot 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 k. So the total number of parameter is k times k plus 1 by 2. So it's of the order of k square by 2 basically, more or less, right? Correct? So total number of parameters is 1 plus 2 plus k, right? Which is equal to k times k plus 1 by 2 of the order of k square by 2, which is actually not small. When the parameter is in square, it is never small, right? You don't want that. You ideally want it to be linear. I mean, right? But it's not. It's not. It's of the order of k square by 2. Okay. So this is the number of parameters that you have. So this basically means that the parameters grows quadratic. I mean, it grows in as square, right? So if the number of feature is million, it is million square. That's what you are looking at, right? So imagine a image of dimension. I mean, high definition image, not even. I mean, nowadays we don't call it high. Let's think about 1000 cross 1000 pixel size. That's a common, very common image nowadays. I mean, now high definition is 4K, right? This is 1K. So 1000 cross 1000. What is the number of features? 1 million. What is the number of parameter? 1 million square by 2, more or less. So you can imagine how this will grow. And this will not be, I mean, this is not a good idea probably to use this. So that's why I've started with this, because yeah, people still use autoregressive, but maybe not in this form. So it's better to start with what is the oldest, right? So this is around 2015 is when I think it was proposed. Actually, more before that, but 15 also people were working on it, I'll say. Okay, so number of parameters is of the order k square by 2. Okay. So suppose now, although I've not discussed it, but let's assume that I have learned the beta. Okay. And I want to now sample, because my ultimate goal, or one of the ultimate goal, is to learn the distribution so that I can sample from it. So I can perform, or not perform, I can generate data without actually performing the experiment. Because the experiments are expensive, I don't want to perform those. So what I want to do is that I will learn the distribution and just sample from it, right? So if you have to sample from the distribution that I've learned following this scheme, and I'm assuming I've already learned, so betas are known. How will I proceed? Any idea? How will I sample from this scheme? Hmm? First, you will sample x1 and from a Bernoulli distribution with parameter alpha 1. Now, condition on that sample, or for that sample, you will calculate alpha 2. And you will sample x2 from Bernoulli with parameter alpha 2. Whatever sample you get, you will now, as a function of that sample, find out alpha 3, right? And now you will draw a sample from Bernoulli with parameter alpha 3. You see why is it called autoregressive? It's exactly what you will do in autoregressive. Whatever you predict in the previous step goes as input in the next step. That is exactly what we are doing. So that's why it is called autoregressive. Okay, that inference or drawing sample is actually autoregressive. Okay, so to sample from this distribution, we follow an autoregressive scheme, right? So step 1 is you will sample, let's call it what, x1 maybe a sample. So you can also call it x1 bar. You will sample it from, I mean, in a generic sense, you will sample it from P of x1, which you have learned. For this MNIST data set, you will sample it from Bernoulli, right? So let's talk about the Bernoulli only. So I'm writing Bernoulli, but in a generic sense, it's not Bernoulli. It need not be Bernoulli always, and you will see cases where it will not be Bernoulli. I mean, whenever it is not black and white, it will not be Bernoulli, right? But let's for now assume it is uh, Bernoulli, okay? Uh, because we are talking about Bernoulli will sample from x1 given alpha 1, right? You will sample x2 from a Bernoulli x2 given alpha 2 as a function of x1 bar. X1 bar is the sample you generated in the previous step, right? Autoregressive, and you continue like that. And let me write also generic one. I mean, this was the specific one, right? In generic case, you will sample x1 bar from some distribution parameterized by theta x1. You will sample x2 bar from, okay, let's call it x1, right? q1, q2 theta x2 given x1, and you continue like that, right? Not x1, x1 bar, and you continue like that, okay? And this theta will be, by the way, this theta I have written same because I am combining them, but actually it will be theta 1, theta 2 will be function of x1 bar, and so on and so forth. But all those parameters as a whole I am writing as theta. Not every theta will appear in all this distribution. Okay. So theta is like, in this case is actually alpha 1, then beta 1, beta 2, beta 3, beta 4. All of those together is theta. So I'm writing theta, but not all theta will be there in all the expression. Okay. So this is how you will sample, right? Any doubt on the sampling part? You can also check that given a sample whether it is in the same distribution or not. So if that is the case, you have already found out it is Bernoulli. You have also already find out P, or which is alpha in this case. Just put that sample value into that and you will get a number which will tell you the probability with which that sample belongs to this distribution. Because in this case it's PMF, so probability mass is probability. So basically if you want to find out what is the probability that a sample I have given you belongs to this distribution from which the data is generated, so a new sample. So if I give you a new sample and ask you, is it from the same distribution? What you will do is that you will take that sample value and put it into this joint distribution, right? And you know the Bernoulli form, P to the power x 1 minus P to the power 1 minus x, where P is equal to alpha. You will put that and evaluate that, and that will give you a probability. It will tell you either, say, a low probability. A low probability will mean that it is not from that distribution. A high probability will mean probably that it is from that distribution. So you can find out, right? And from there you can detect whether that is an anomaly or not. If it does not belong to the distribution, then it's an anomaly. uh, it's not there. Hmm? Thresholding of what? Okay, that's a subjective decision you have to take. So generally, let's say you decide, right, for a problem. Generally, 0.5 is obviously a very obvious choice, but 0.5 is not a good choice, I'll say. So you will say 0.5, I don't know it belongs to or not. Maybe 0.75 and above, okay, it probably belongs. Point. Hmm. Yes, there are different ways of doing the threshold. So, and one way is obviously to look at the data set. One way is to keep a validation set. And from the validation set, you see when it belongs, what is the threshold, when it does not belong, what is the threshold, and find from that. So there are ways of doing that, but ultimately it's a subjective decision because, or it's a grid search kind of decision. You don't train for it, I mean, what I mean. You will not train for it. You can either do it based on validation, which is like a grid search or whatever you call it, right? Or you will do it based on your own experience in that domain, in that sense. Okay. And that threshold is very problem dependent. It will change from problem to problem, as you correctly pointed out. Okay. But yeah, but you can do it. I mean, you can find out the probability, and based on that, you can decide whether it belongs to something or not. Okay. Any question? At least on the Bernoulli part, the right hand side, if you don't follow, that's fine. That will become clear probably in a short while. But the Bernoulli and the MNIST data set, is it fine? Okay. So, okay, but it has a name, by the way. It is called fully visible sigmoid belief network or something like that, or deep belief network. Uh, so ABSBN or something is FBSBN. So I think fully visible sigmoid or sigmoid belief network. That's what this algorithm is called. Okay, but how does it perform? So let's go here. Yeah, full FSBN, right? FVSBN, which is fully visible sigmoid belief network, is what you call this method. Okay, fully visible because you have observed everything. And what do I mean by observed everything will become clear in a short while when I go to the next algorithm. Uh, sigmoid belief network comes from the Bayesian network part. And in Bayesian network, because you are using the sigmoid function, so logistic regression, so sigmoid belief network. So that's why you call it fully visible, because there is no hidden layer as such. There is no neural network, so to say. So that's why fully visible. Sigmoid belief network, because belief network is coming from, because we're doing that conditional distribution, right? Just like a probabilistic graphical model, a Bayesian network. So that's why belief network. And sigmoid, because we are using the sigmoid in the logistic regression. Okay. But I did not came to this slide to tell you the name that you could have seen. I came to this slide to show you the results. And it does not really work that well, right? The left one is a true data. The right one is samples drawn from this fully visible sigmoid belief network. And it does not really do that well, right? It's quite obvious from the figure on the right that the performance is not uh, up to the mark. Why is it so? What do you think is the reason that the performance is not so good? What do you think is the limiting factor in what we are discussing? In this thing, what do you think is the limiting factor? Right now, no. Right now, we're not doing conditional. We're not doing that. Will come later. Okay. So, in every algorithm that we discuss in this course, we'll first discuss the unconditional one. Conditional is always a special case of or an improvement over, let's say. So, right now, no. It's all unconditional right now. No, I mean, you cannot talk. I mean, so my goal is to generate unconditional. So, you cannot say it is not generating unconditional because I'm not doing conditional. Because my goal itself is to learn the total distribution, right? No, no. So vanishing gradient problem I will not ask today, obviously, if that was the reason, because I'm not even gone to training. So the reason should not be something related to training. The reason is something else, obviously. I mean, it should not be something related to training. Then, yet I understand what you're saying. That vanishing gradient can be a problem because of the autoregressive nature, but you don't even know how we train it. How do you know vanishing gradient will come? Maybe I'll train it separately. Each of this, right? I understand what you're saying because autoregressive, so RNN kind of structure, so vanishing gradient. Uh, I understand, but we have not even discussed how we train it. I mean, we need not train all of this. Maybe we are able to train this parallelly. Who knows? The reason is quite obvious actually, and the reason is this second last expression. We are approximating it using a single layer, logistic regression, and that is not expressive enough. I mean, we know that, right? That logistic regression, if it was so good, we should not be needing neural network in the first place, right? So the reason is this: what you were saying, that each of these conditionals or the parameters of the conditionals, we are approximating or trying to find out using logistic regression, which is like a single, I mean, not even layer, I mean, just a linear and a sigmoid, right? That is the bottleneck. The solution is make it a neural network. And that's what the next algorithm talks about. The next algorithm, which is an improvement over this, the idea is very simple. We will do the exact same thing autoregressive way, but this expression, alpha as a function of x and beta, this will not be a sigmoid, or this will still be a sigmoid, but this will not be a logistic regression. This will rather be a single layer or single hidden layer neural network. If I make it a single hidden layer neural network, it should still work, and we'll see what happens. Okay. So, yeah. So performance of fully visible sigmoid belief network is often not good. Okay. Performance of fully visible sigmoid belief network is often uh, not good or not up to the mark. And the bottleneck, I mean, the common suspect, if I may call it, is the logistic regression that is sitting and being tasked with finding the alphas. And one potential reason is the logistic regression used to compute alphas. Okay. One potential reason. There can be other reasons also, but one potential reason is that one. And if that is a potential reason, obvious thing to do is to replace it with a simple neural network, a shallow neural network, and see how it does. And people did it, right? So therefore, we replace logistic regression with single layer. And when I say single layer, keep in mind it's hidden layer. Okay. So that's hidden actually. Neural network. Okay. So replace it with a single layer neural network, which means it's one hidden, the input, one hidden layer and the output. So that's what single layer is, okay. And the idea is that that will allow it to learn better, because the hidden layer will extract features in high dimensional space, and that will then go into the sigmoid or logistic, and that will probably perform better. We know that when you uplift, you get features where learning becomes easier. That's a well known fact in deep learning. So the idea is to use the same concept, okay. Therefore, we replace logistic regression with single layer hidden neural network, and which means that, what was the expression I forgot? Alpha, right? Alpha j. Therefore, alpha j as a function of x less than j is fundamentally a neural network uh, parameterized by theta, uh, and its function of x 1 to j minus 1. Okay, it's function of x1 to j minus 1, and it's a single layer. So if I have to write it down, I mean, using the notation, it will be something like sigma 2 operating on, let's call it, what is the notation should I use? Let's see, beta maybe we should use. So yeah, beta. Okay, let's sigma 2 operating on beta 2 j operating on sigma 1 operating on beta 1 j operating on x 1 to j minus 1. Okay, Bhagis. Okay, x 1 to j minus 1. Okay, clear? This is what it is. I mean, this expression I talked about in the practical, right? So you know that it means that's composition of function basically, sigma of beta of sigma of, right? Now in this case, what will be sigma 2? If you are talking about the MNIST data set, which is like the Bernoulli case, then sigma 2 will have to be sigmoid. So sigma 2 will be sigmoid, that will not change. But sigma 1 is now flexible. You decide. You use ReLU, ELU, GELU, whatever you want. Means you can decide that. Okay. Apart from that, you can also decide the hidden layer dimension, the depth of the hidden layer. How many nodes will be there in the hidden layer is a parameter for you, hyperparameter for you to now decide. And you decide that as well. You get to decide that, and that can improve your result. So this is the only change that was done, a change that was done. This is known as, I forgot the name again, neural autoregressive density estimate, NAD. Okay, this is known as neural autoregressive density estimation. Autoregressive density estimation is obvious. Neural, because you are using neural network. I actually forgot what comes first, autoregressive neural or neural autoregressive, but yeah. Probability density. No, again, you're forgetting. This, like this one is not limited to only Bernoulli. I am giving the example of Bernoulli. Think about it, it can be continuous also, right? I mean, this framework will not change. So that's why. Okay, so this is known as neural autoregressive density estimation. So when you replace this sigmoid by neural network, it becomes, or logistic by neural network, it becomes neural autoregressive density estimation. So what happened? This is known as NAD. Okay. and check it. I think in the slide the citation was given, but I think this paper came out in 2016 or so. I mean, okay. Neural autoregressive, and I think this is something where this deep learning, machine learning, AI community is unique, because if in other domain a paper had come out in 2016, that would have been the state of the art. Probably the course would have ended with that. Whereas in machine learning and deep learning, we start the course with something that came out in 2016, and it will probably end with flow matching, which came out in 2021, 22, something like that, or at least became popular at that time. So that's a very critical difference between a course on machine learning, deep learning versus some other course. It's so fast paced that the syllabus keeps on changing. I mean, I don't know if in 3 years I teach this course, what will I be teaching? Maybe I'll not even cover this need. I'll start from maybe diffusion and go somewhere else, and who knows, right? So this is a domain where you needs to be updated all the time. If you're not on your toes, you are not up to the date to what is happening. Okay. Neural autoregressive density estimation. Okay. So in this case, there is one more thing in NAID I want to discuss before I move ahead. Actually, this is not exactly NAID. There is a subtle change that is there, but let us come to that. So remember that we are using the neural network to find out what? To find out the alphas, right? Which is the probability of success, at least till now. And this probability of success alpha, we are using neural network to find. So let us write down the first 2, 3 alphas and see how it will look with neural network into picture now. Okay. So let's start with alpha 2. Alpha 1 does not change. That is the unconditional or the marginal one. So let's start with alpha 2, which is probability of x2 given x1, right? So let's try. So let's talk about alpha 2, and it is function of only x1. So remember, I am using neural network, right? So alpha 2 will not directly be function of x1. I mean, it will be, but it will be via h. So first I should write it in terms of h, and then I will write h in terms of x1. That's what we did in neural network, and that's what we do in neural network, right? So sigma 2, okay, and then beta 2, uh, because alpha 2, so I'm using beta 2, and let's include the bias into beta, or let's say assume there is no bias. Okay, bias is not there, and let's make our life simple. So beta 2 transpose h, okay, and this h I will call it h1. This is how it will look, right? I mean, plus b, I'm not writing the bias. Okay. I mean, h1 is equal to sigma 1, yeah, beta 2 and beta 1 will create problem, I can see. So I'm thinking what to call it. Let's call it beta 2 2. Okay, I'm calling it beta 2 2. So this will become beta 1 2 transpose x1. So the subscript 1 denotes that is the first layer, weights associated with the first layer. The superscript 2, which is constant, denotes that I am finding out alpha 2. Because I will also find out alpha 3, alpha 4, alpha 5. And if I am not careful, I mean, those notations will get mixed up. I will have to use the same notation. So the superscript denote that I am finding out alpha 2 and not alpha 3, alpha 4, alpha 5. The subscript denotes that which hidden layer I am in, I mean the first or the second. Clear? The notation is clear? So when you see beta 1 2, 1 in subscript, 2 in superscript, it means that it's the first layer weight. I mean, input to hidden layer for finding out alpha 2. Beta 1, 3 will be first layer weight for finding out alpha 3. Beta 1, 4 will be first layer for finding out alpha 4. Similarly, beta 2, 2 will be second layer weights for finding out alpha 2. Beta 2, 4 will be second layer weights for finding out alpha 4. So the notation is clear what I am doing? Please write it down. I am not writing it so that otherwise you will get confused with the notation. Okay. This is how it will look. And if I look at the dimension, how will it look? Let us write down the dimensions. So for finding out the dimension of the number of weights, basically I am trying to find out the number of parameters. Okay. To find out the number of parameters, we need to fix the hidden layer dimension. Okay. Let's assume that the hidden layer dimension is D, capital D. It can be M also, but let's assume it D. So we assume that, okay, I think I should also write H12 here. Okay. We assume that H12, so basically there are D hidden nodes. That's all it means. There are D nodes in the hidden layer. Okay. Okay. So that is the case. So now let us start from here. Sigma 2, beta 22. What is the dimension of beta 22? Beta 22. It is a vector, is it a matrix? How many elements? D, right? 1 cross D and D cross 1 will become 1 cross 1. So this is something like this, which is 1 cross D, and H is D cross 1. Right? So my unknowns is 1 cross D right now. H12, it's sigma 1. Beta 2, beta 1, 2, what is the dimension? X1 is the first one, right? So it's only 1. X, because next I'll write X1 to 1 to 2, so that will become 2. So X1 is actually 1. So this will be equal to D cross 1 and 1 cross 1, that will give me D cross 1, right? This is D cross 1 multiplied by 1 cross 1, right? Multiplied by what? X1. Everyone follows? D cross 1 and 1 cross 1, so D cross 1 is what you get. Now this will change when I go to alpha 3. So alpha 3, I will not write the first line, but I will directly write the second line, which is the dimension. Alpha 3 is function of what? X1, X2, exactly. This is equal to sigma 2. Anything will change in this one? H dimension is same. Will anything change? No, because alpha 2 is also a scalar. Alpha 3 is also a scalar. So this will not change. 1 cross D, and this will be D cross 1. Let's come here. What will happen here? What is the dimension? Now X dimension is 2, X1 and X2. So the weight dimension will be D cross 2. D cross 2 and 2 cross 1. That will give you D cross 1. And then here you have D cross 2, 2 cross 1, right? So X1. Repeat. Correct. H1 3, right? Yes. This one. Yes. Thank you. Clear? Now you can imagine that if I go ahead, this will keep on increasing. So what is the number of parameters I have now? If I have k such alphas, let's assume k such alphas, so then see the second one will remain. So it will be 1 cross d. So d, so kd, the second or the first one rather in this case, which is actually second. So that 1 cross d, that does not change. So if I have k times, it will be kd. Correct? First one is now increasing. D, 2d, 3d, kd. So d multiplied by k times k plus 1 by 2. Correct? So the total parameters is kd plus k times d, this d plus 1 by 2. So I can say the order is of kd square. I will take the highest one. So kd square, because d into d plus 1 by 2 is like d square, and plus, yeah, I mean, so right, dk square, correct, thank you. Dk square, not kd square, k square d, right? That will be the order. This again is quite high. And with this many parameter, what happens specifically in neural network is that you have a tendency of overfitting, right? So what is generally done in NAD, which is the neural autoregressive density estimation, is that you have parameter sharing. Parameter sharing or tying the parameters. I'll tell you how it is done. Okay, that's why I wrote all of this. I mean, to find out this kd plus k d into k plus k into k plus 1, I did not need to write this thing, right? So number of parameters is kd plus uh, k plus 1 by 2 d, which is approximately of the order of k o k square d, something like that, right? It is of the order of that. Okay, which again is quadratic in k, and now d is also coming into picture, so it is actually quite high. So now I said that with so much parameter, there is a general tendency of overfitting. Overfitting, again, we discussed it in the practical, right? Uh, so with such large number of parameters, it can overfit. Okay. So the solution is parameter sharing. How is parameter sharing happening? I'll tell you. Okay. So solution parameter sharing. Okay. The solution is parameter sharing. Now I am going to write the parameter sharing in colors, in different colors, so that it is easy. Otherwise, it will be little difficult to follow. So what I want you to focus on is the weight matrix with sigma 1, because that is the matrix that is increasing. The other matrix, let us not care about that. Let us only focus on the weight matrix associated with uh, sigma 1, which is the weight that will give you the hidden nodes. Okay. So we will only focus on that d cross 1, d cross 2, and all of those things. Okay. So how parameter sharing happens? So when I have h12, right? h12, right? It is sigma 1. Okay. And let's call this matrix as, or in this case vector, as we are using beta, right? So let's use beta. Sigma 1 beta 1 2 transpose x1. Okay. And beta 1 2, what is the dimension? 1 cross D, transpose will become D cross 1. So 1 cross D. And if I do not write the transpose, then it is D cross 1. Let us write. So what I will like you to focus on is this term. This term. Keep this in mind. Okay. So now we write H13. This is sigma 1. And now what is the matrix size I need? D cross 2, right? That D cross 2 matrix will come. So this D cross 1 that I got remains same. So I just add one more column or row. Depends how you are looking at with or without transpose. So based on that. So I'll add just one more learnable parameter, one column. The previous one is the same as what I use for alpha 2. So parameter sharing or parameter time. So this will now be equal to beta 1 2 and then beta 1 3 transpose x1 x2. Where this one and this one are actually same. So they are sharing parameters, these two are same. So what is new that I have added? Only beta 2 3. And what is the dimension of this new thing I have added? D cross 1. So that means for every new alphas I only add D cross 1. So then the number of parameters becomes kd. So instead of k squared d, it now becomes kd. Clear? So the number of parameter reduces, training becomes obviously easier, the chances of overfitting reduces, and it becomes faster, and it works hopefully. Okay. So I will write one more, which is H14, so that we. No, I've written a transpose there. Each of these, what is the dimension of B12? 1 cross D. So whatever I understand what you are saying, so it will be actually semicolon. This one should be semicolon. Semicolons means like this. It is like this, you rotate it, it becomes one of this becomes right. So this is like, yeah, this is like this and this. Each of this is a row, and you transpose it, it becomes column. Okay, so that's why we written the semicolon. Take a note of the semicolon. That means they are different rows. Okay, so now let us also write H14. So H14 is sigma 1, and then you have beta 1 2 semicolon beta 1 3 semicolon beta 1 4 transpose x1 x2 x3. Okay, and then this is exactly same as this, right? So all the violet colors are having the same thing, and then green, right? This and this are again same. And third one is the only new thing you have added. And with this setup, the number of parameters is kd. So this is the node actually. Okay, this is the node, and here the parameter is of the order of k d. Okay. Yeah. We'll do that next time. So yeah, but you are right. We have to do it like that, right? Um, yes. Obviously, there are other ways of using CNN and all of those things are there, but I'm not going to CNN right now. But yeah. Not really, because see, you are fixing it, but finding this beta, new beta, does not depend on the previous beta. I mean, it not directly dependent, indirectly depends, because you fixed it so that values will be a function of that. But directly, it's not a direct function of that. So it's not autoregressive in that sense. Yes, the final betas are. Yeah. Okay. Any doubt? If there is no doubt, I have to. I mean, I don't have time, but I'll use maybe 5-6 minutes more and just tell you how to generalize it to other things. So remember, all of this we discussed about is only for Bernoulli, binary, 0 and 1. Real life is not so kind to us. We will not have 0 and 1. Even images, I mean, if it is not black and white, we have pixel values from 0 to 255. So non-binary discrete variable, how will you do it? If it is non-binary discrete variable, then let us start from here, right? Let us go back. Non-discrete Bernoulli variable, this Bernoulli distribution will not hold. Bernoulli will become multinolly, or yeah, categorical as you call it, right? Which is the throwing a dice. So this Bernoulli will become multinolly. I think in the slide it is written Dirichlet. So I have to correct it. Multinolly's conjugate prior is Dirichlet, but yeah, it's multinolly distribution, which is the throwing a dice. So or categorical. So each of the Bernoulli distribution will become categorical distribution. And the number of parameter space will obviously increase for categorical. Uh, the number of independent parameter for categorical is m minus 1, where m is the number of categories. This is clear. One more thing will change in the neural network. Your last layer from sigmoid will become softmax. So there is only two changes you will need to do for discrete non-binary case. First change is that it's no longer Bernoulli, it's categorical, which is multinolly. The second thing is that the neural network, instead of sigmoid in the last layer, middle layer relu melu will stay, doesn't matter. The last one instead of sigmoid will become now softmax. So softmax is for multi-class, right? And that's all. Okay. Oh. Okay, there are two things, right? It is effective because uh, you are basically saying, by making it same, that only one, changing only one is enough to learn that. Fundamentally, you are saying that. No, you cannot, because you see, it is not logistic. There is one more layer. This is what you are doing here is not in the last layer. This is because you have to remember that this layer is only giving you the features. Your act, and then after that there is the sigmoid layer which you are not touching. So what this is doing is that it is making your features kind of little bit uh, or non-optimal. The features that you are learning are now not optimal. But then there is this whole line of work which is known as extreme learning machine, where the features are actually random. What you do in extreme learning machine is that you make all the weights of the first layer random. And it works because the idea is that no matter what features you are giving, it is function of x. And your second layer will learn that based on that features. So here what is happening is that the features are now not optimal. And because they are not optimal, they will not be fitting the data exactly. And because they are not fitting the data exactly, which is noisy by the way, you will not overfit. Exactly, it is better because your number of features has increased. the number of features has increased, right? And also it is better because your number of parameters has reduced, even from Bernoulli, that logistic case, right? I mean, assuming D is much less than K, then it is not K square any longer. If D is much less than K, then it's also effective. So I'll repeat once more. For categorical or non-binary discrete case, your Bernoulli will become categorical. Your sigmoid in the last layer, not sigma 1, sigma 2. Where is sigma 2? There. Sigma 2 will become softmax. A more generic case, what will happen if it is continuous? If it is continuous, then you are in trouble, because then you do not know what continuous random variable to use. I mean, is it Bernoulli? I mean, it is Gaussian? Is it student's T? Is it uniform? You do not know that. So in that case, now you have to take a judgmental call, that what do you think for your data is the best thing. The one that is generally used is mixture of Gaussian, because mixture of Gaussian is very flexible and can approximate any distribution. If you have k mixtures, you can have k modal, so 1 to k modes you can capture. We'll talk about it next lecture also, but just to wrap these things up, because we'll meet in 1 week. So if it is Gaussian, if it is continuous, what you will do is that you will assume, let's say, mixture of Gaussian, and let your neural network predict the parameters of that: mean, standard deviation, and even the, if you want, even the mixing parameters, even that can be. So in that case, your neural network will predict the means actually, each mixture variances, each mixture, and the mixing coefficients. Categorical and continuous I will again discuss next time, but we are pretty much done with the Bernoulli case. Okay, any question? So basically in the features of a data point, putting it in a neural network and trying to find the alpha for this specific case, the LNS case. So how do we generate data? You don't generate. How do you generate data after you've learned it? Or how do you generate data for training? No, you don't generate. You have been given data. If you are generating data, that means you know the distributions, and then the whole point of generative modeling is out of the picture. The idea of generative modeling is that you don't know what data has come from, you have been given data. Your objective is to learn the distribution and generate new data, right? So you don't generate, you have been given data. Like MNIST, you don't know how it has been generated. You know it's handwritten or something, but that's all. Okay. All alphas? I mean, why do you think that we will not use MLE for determining alpha? Maybe we'll use MLE next time. We have not done it yet. What you are trying to ask is that why not the classical MLE, right? Because these alphas are function of x. It's conditional distribution. So alphas are function of x. So you have to write alpha as a function of x. Alpha is not independent of x. You have the data, but do you have data where, how many data you will have where x784 is conditioned on different values of 1 to 783? You will not even have one data on that, because there is so many conditioning, you will probably not have any data on that. So what you are talking about is actually conditional probability table, right? That we can do, and that is the optimal one if we have infinite data. Because if I have infinite data, then I have all possibilities. So then you do that conditional probability table, find MLE, conditional probability table numbers, entries using MLEs, and you are fine. But you don't have that. You will never have that. And so these things comes into picture. Because of conditionals. If it is like P of X, right, the first one, that probably will do MLE. What I was suggesting was MLE, right? Count how many. For that you can. But for the conditional ones, and the further you go in that chain, it becomes almost impossible. Right? Okay. Any other question? Thank you.